Hello everyone. Today we are going to discuss the very basics of heat conduction, specifically the Fourier law of heat conduction in 1D and 3D. Then we'll continue with the unsteady state heat conduction equation, the diffusion equation. So very basic equations I'll be discussing today. If you want anything in specific in heat transfer, you can comment me below. So let us consider the case of conduction in one dimension. So let us draw a xy coordinate system here and let us draw a slab. I'm trying to use a different pen here. Let us draw a slab, but yeah, my lines are not straight. So okay, that looks acceptable. So let's say through the slab the heat conduction is happening in the x direction. For such a situation, if you have a system where heat transfer is happening in the x direction, how can we write the heat flux, the conduction heat flux, also called diffusion heat flux in x direction? That can be written as, the heat flux here can be written as a function of the thermal conductivity and the thermal gradient, as we know already. So anyone who is familiar with heat transfer knows this equation, which is Qx, which is the heat flux in x direction, equals to minus K dt dx. Let's call this equation as equation number 1. So in this equation, the left hand side term Qx is the conductive flux, sometimes also called diffusive flux. In the right hand side, K is the thermal conductivity of the material, solid material here, and the differential that you see is the thermal or temperature gradient. The minus sign here depicts the heat transfer happens in the decreasing direction of temperature. Now let us consider a situation where we have a three-dimensional slab. So I'm trying to draw a 3D slab here using a Cartesian coordinate system of x, y, and z coordinates. So let's consider, my line is not very straight here. Let me draw a straight line. Okay, that looks to be okay. Okay, let us draw a 3D slab which looks very 3D. I'm not very good at drawing, but I'll try. So in this direction, we have the heat transfer in x direction. So here we have the y direction heat transfer, and here we have the z direction heat transfer. All are the conduction heat transfers. So similar to the previous equation, if we want to write the heat flux in y and z direction, we have to take the thermal conductivity into consideration as well as the thermal gradient into consideration, which can be written as follows here. Which is Qy, which is the heat flux in y direction, will be equals to minus K dt dy, and that's equation number 2. Let's say Qz is minus K dt dz. So one thing I want to make clear here, that I have assumed the thermal conductivity to be constant and it's not a function of space here. That's why in all three equations I have written thermal conductivity as K, but in reality that's not the case. So I'll also write another sentence here. Equation 1, 2 and 3 are written for isotropic system or isotropic material. The thermal conductivity of the material here is constant with space. If this is not the case, then we should have written different thermal conductivities for different equations. So now, if you want to combine equations 1, 2 and 3, and after combining, if you want to write them in a vector form, what we are what we will get. So if you want to know more about vector analysis, you can tell me. I can prepare a lecture on that. So q bar, whenever I'm putting a bar, that's a vector, equals to ex qx plus ey qy plus ez qc. Let's number this equation as equation number, I think it will be 4. Yeah. So q here is, with the bar below, is the heat flux vector, which is having 3 components, and in the right hand side, ex, ey and ez with the bar below are vectors. These are the unit normal vectors in the respective directions, as you can see in the subscript. Okay, so this is the heat flux vector. Now if you want to substitute qx, qy and qz here, we can write ex dt dx plus ey dt dy and plus ez dt dz. Let us number this equation as equation number 5, and then we'll get q equals to minus k del t. See, here I have put a bar below del because that is a vector operator. It's very interesting though. If you want to know more about that, I can discuss. So look at equation number 1 here. The equation number 1 here, as you know, is the Fourier's law of heat conduction in one dimension. This is a very basic equation. Whenever you have heat transfer, you do study that. And equation number 5 here is the Fourier's law of heat conduction in 3 dimension. In 3 dimensions. Yeah. So in this case, I have already mentioned before, K is here the thermal conductivity, and here we have obtained this as a constant, but in general it would be constant or variable. It's very important whenever we discuss about insulation of anything, starting for your mobile phone to the building, to anything, the thermos or any other material that is used for thermal insulation in industry as well as at home. It can be a variable or a constant, which I have already mentioned before. The values of thermal conductivity is very diverse, that can range from 0.01 watts per meter Kelvin, that's the unit of thermal conductivity. This is for carbon dioxide gas. It can go till a value as high as 1000 watts per meter Kelvin for a very conductive material such as silver. So in general, if we look at matters, the thermal conductivity of gas and liquids and solids are different. The gas thermal conductivity is generally less than the liquid thermal conductivity, which is further less than the solid thermal conductivity. And there are different ranges of values of thermal conductivity for gas that ranges from 0.01 to 1 watts per meter Kelvin. For liquid, it ranges from 1 to 10 watts per meter Kelvin. And for solid, it ranges from 10 to 1000 watts per meter Kelvin. These values has very significant molecular implications. If you want to know more about that, you can let me know. I will record a lecture on that. So on that topic, let us discuss a little bit about the diffusion equation, which you already know before, but let us have an overview on that. Let us consider a system without any fluid flow and without any external heat generation. And I am not mentioning here, so it is a unsteady state conduction system. So if you write an energy balance equation for such a system in 3 dimension, it will generally look like this. Rho Cp dt d small t equals to minus del dot q, where q is the heat flux vector that we have discussed before. Let's number this equation as equation number 6, continuing from the previous notes. Rho here is the density of the material through which conduction is happening. Cp is the heat capacity at constant pressure here, and dt constant pressure, and dt is the substantial or material derivative. We do have very interesting explanation of this. Let me know if you want to know more about it. And q, of course, we know this as the heat flux vector, which we have discussed in few minutes back. So if we substitute q and write it in terms of the temperature gradient, or substitute the Fourier's law of heat conduction, it will look like this: k del T. Let's name this equation, number this equation as it will be equation number 7. Then this equation can be written as rho Cp dt dt equals to del square T. If it is k is a constant, k can be taken outside. You already know that k is the thermal conductivity, which is constant in this case, and because of that we are able to bring k outside of the bracket here. It's not a function of space. Then let us look at the left hand side. The left hand side can be written as rho Cp d dou t, the partial derivative, equals to k del square T. Because there is no flow, it can be written like this. If there is flow, then it may not be. Then rho Cp dou t can be written as k dou square T dou x square plus dou square T dou y square plus dou square T dou z square. Let us number this as equation number 10. Very interesting equation, very very important equation. Let us take the rho Cp in the left hand side to the right hand side, and equation number 10 becomes dou t equals to k divided by rho Cp multiplied by dou square T dou x square plus dou square T dou y square plus dou square T dou z square. This is equation number 11. Look at k by rho Cp. It's a very interesting term, which is also called, if you remember, k by rho Cp equals to alpha, which is the thermal diffusivity. Thermal diffusivity. Okay. Equation number 11 is a very important equation, and if you want to write this equation, let's say at steady state, then the entire left hand side will go 0, and the equation will become dou square T dou x square plus dou square T dou y square plus dou square T dou z square equals to 0. This is for Cartesian coordinate system. This is the steady state conduction equation in 3D. If you want to know more about any other topic of heat transfer, you can always write it in the comment. I'll try to make some lecture on it. So thank you for sticking up till now. We'll see you next time if I come back. Bye bye.